Okay, here we go. This is the activity report for the Coral Reef task team. And as you can see, Jonathan's been a busy man. So there's three aspects to this, three activities basically. We have been slowly working on updating the Coral Heat Stress SST user requirements document. I'll speak to that. Then I'll talk about the investigation into the strengths and weaknesses of physical retrieval versus regression-based SST over coral reefs. This is very preliminary work, but as you'll see, there looks like there's an interesting story. And then Jonathan will complete the talk with a couple of slides looking at the work we've been doing on using metrology to understand the uncertainties in satellite-based coral heat stress monitoring tools. So as far as our user requirements document, there's three things we've been working on updating. The first one is to talk about the SST resolution. Previously, we've said 5K is good enough, but the extreme marine heat wave in the Caribbean at the moment, and likely down here in Australia soon, and then it'll probably end up everywhere eventually this year. Well, this year, next year. Has highlighted the fact that we need higher resolution data. In effect, our products, the 5K products, basically said that almost every coral reef, every coral, I should say, in the entire Caribbean, Greater Caribbean I'm talking about, should have cooked, but they didn't. Not all of them, at least. Most of them did, but a few survived. It would be really cool to be able to see the higher resolution, so down to around 100 meter resolution sort of thing. And that means that we want it to be continuous, so a level 4 product. So that will be somewhat challenging, but Chris has some ideas as usual. We're going to update the section on diurnal SST needs. Previously, we've said nighttime SST is good enough, but we are now chasing mortality products. So previously, we've looked at just using SST to predict when and how severe a bleaching event occurs. And we now want to chase a mortality product, which looks like being just SST as opposed to SST and light. And it is likely to need daytime temperatures as well. So we need to understand, we need to have good SSTs in the day and at night. And partially this is the reason why we're working on the looking at the comparison between the two algorithms. And then lastly, we currently cover pretty well all of marine biological needs in all oceans, not just corals, except the polar waters when it comes to our user requirements document. So I've enlisted a couple of people that work in the polar regions to help us update that. And as you could expect, it's mostly a sea ice story and how they would like us to cope with that for them. Okay, now for the second activity that we've been working on. This is very new stuff. Some of the co-authors on what will eventually be a paper haven't even seen this yet, so some of you are ahead of them. So what we're doing is, initially at least, having a look at the difference between physical retrieval and regression-based algorithms over the top of coral reefs. Our example of physical retrieval algorithm in this first look is CCI, and Chris was nice enough to give us some level 3 AVHR3 data from NOAA 19, MEDOP A and MEDOP B. For the regression-based data, we're using AXPO as our example, and CrossNJet's given us some level 3 VIIRs from NPP. I guess the first thing that jump out at you was the fact that they're not exact matchups in comparisons, and that's okay. This is only a first look. The question was, do we spend a lot of time on this, or do we not bother? And you'll see at the end it's worth bothering. So we have 3 different sites we had to look at. Arlington Reef in the Great Barrier Reef is just off Cairns, just north of where I live, and it is a high tidal range region. The Dry Tortugas over in the Florida Keys, right at the very end of the Florida Keys, is a low tidal range example, but it's a reef as well. So Arlington and Dry Tortugas were satellite data sitting on top of a reef. And then Redcliffe Bay, although there are reefs around, this is really a shallow water example. So I've got 3 examples of the 3 different ocean types that we've got right next to and in and around coral reefs to have a look at. And they spit up some really interesting stuff. So let's get into it. Arlington Reef, up near Cairns. There's Cairns and there's Arlington Reef. This is a big reef, actually. If you have a look down the bottom left, you'll see that it's many kilometres, tens of kilometres across. In fact, in that one reef, they've got 3 other reefs that have been named, which really should have been part of Arlington Reef. So that's interesting in its own right. The temperature logger data is sitting on top of, or close, about 2 metre deep water. Bear in mind, this is about a 4.5 metre tidal range. So that 2 metres moves around a little bit, but on average, it's about 2 metre deep water. And the satellite pixels were just in from there. Later on, we'll do a better job of matching the two up. But you'll see that this isn't a big issue. This is a very well-mixed region. So these are, you're going to see these over and over again in this talk. So I'll explain a little bit. So we've got the logger data is on the x-axis, the satellite data is on the y-axis, and the red line is the 45-degree line, or the 1-to-1 line. And so when you see a point that's above the line, that means the satellite was too warm. When you see a point that's below the line, that means the satellite was too cool. So for nighttime, first thing that springs to mind is that CCI was having some cloud contamination issues, possibly, and AXPO did remarkably well, very impressive. The thing to point out, though, is that corals, generally speaking, won't get stressed until they go past the thermal threshold. The accepted thermal threshold at the moment is being defined by Coral Reef Watch, the group that I work for, and it's called the MMM. It's basically the maximum monthly mean, or the average hottest month over a period, and in this case it's 1985 through to 2012. Well, not this case, that's what the MMM is literally defined as. So that means we're only interested in these pixels in this instance. So I looked at the average bias using just the pixels above MMM. In other words, the satellite data minus the logger data. And with that, you can see that VIIRs did very well. I guess you could say that CCI isn't too bad, although MEDOP A is getting a little bit large in its bias. So now during the day, you can see that CCI basically does a fairly good job. However, AXPO tends to overestimate in the higher temperatures. And if we have a look at the MMM, again, all the values over the MMM, and look at those, you can see that VIRS Expo is a little on the high side as far as the bias is concerned. MEDOP A is negative bias, a little bit smaller than the bias in VIRS, which is positive, of course. And MEDOP B is not too bad, and NOAA 19 it was pretty well non-existent. So on average, CCI did better than VIRS in that instance. Than Expo. Okay, over in the dry talk 2. So that was a well-mixed region with high tidal range. So there's going to be a lot of currents to mix things up. Dry talk 2 is stuck out in the middle of nowhere, off the end of the Florida Keys. It's basically considered the very end of the Florida Keys. The logger in this instance is also close to the outer edge of the reef, but sitting on the reef. And we got the satellite pixels from inside, well inside. I was more concerned about making sure we didn't get any oceanic water in there, that it was real reef water. So this is the data, and this is nighttime. So a little bit of cloud contamination, but not much. By and large, they all look pretty good. And of course, Expo once again performed extremely well at night. This is really pleasing, I might add. Looking at the MMM, which is 29.59 degrees in this spot, we're interested in those data, then that's a very pleasing bias analysis for any site, quite frankly. But interesting enough that CCI is holding its own quite well. It will be interesting when we get to comparing Expo and CCI on exactly the same satellites, exactly the same pixel. And for the daytime data, once again, CCI does well, and it doesn't look like there's substantial bias. However, Expo initially looks pretty good when you first glance at it. Then you look a little bit closer and you realize that once again, in the higher SSTs, it's mostly above the line. So when you look at the bias analysis, you can see that Expo once again is warmer during the day than it should be, and CCI has done really well. So Redcliffe Bay, this one's an interesting one. So we're over in WA now, Western Australia that is, and Shark Bay, which is a fantastic place to visit if you're ever over in Australia. There's dolphins. Monkey Mire is the place to go and visit if you want to interact with wild dolphins. They're friendly though, thanks to the tourists feeding them, I think. Redcliffe Bay is, well, Shark Bay is very complex, and Redcliffe Bay is located within Shark Bay, and the logger is sitting on the outer edge of the down the reef slope a little bit, so is very much exposed to the bay waters, and the pixels were offshore a little bit just to make sure that we retrieved shallow water data rather than reef data. And these are the data, these are the results. So nighttime looks very, very similar to one another, and with an MMM of 26.01, you can see that that's a fairly pleasing result. Not too bad. Interestingly enough, VIRS, this is the first time VIRS doesn't sparkle at night, I might add. So that's an interesting question. Is this a consistent thing across all shallow water, not on a reef, or is this a one-off? We'll have to go find out. And for the daytime, this is a real weird one. You can see the CCI on MEDOP A and MEDOP B look great, and indeed you'll see in a minute that it is great. Axpo does the same story for daytime and is on the warm side at the higher end. In fact, it's on the warm side right down the temperature range. The odd thing here, and this is odd because it's out of character given the other locations, CCI on NOAA 19 is all above the line. So I can't help thinking there's something screwy gone on with that particular set of retrievals, but this is something that will be intriguing to try and work out what's gone on. Why is it like that? Looks pretty much the same as Axpo, doesn't it? So if we have a look at the bias here, you can see that MEDOP A and MEDOP B with CCI works very well. VIIRS on NPP, sorry, Axpo on VIIRS is not too good, in fact, quite terrible. And quite frankly, NOAA 19 with CCI is not too far behind. So if we have a look at them all together, you can fairly clearly see that generally speaking, in the daytime, at nighttime, not a massive difference between them, and you'd probably be happy to blend those into a level 4 product, and indeed that's what Andy does for us. So from that perspective, I'm really happy that we're using nighttime only, and bear in mind, we don't have shallow water in our products. In terms of the coral reef products, we tend to stick to the reef pixels. So you blend those, and you'll get a fairly nice product. However, during the day, and if you recall, we wanting to chase daytime data. It looks like we might be tempted to lean towards wanting to use something like CCI, although it's still early days in this analysis, but it certainly looks like Axpo has a tendency to want to overestimate the SSTs during the day, but really good at night, so I'm quite happy with that. So next steps, basically, we've convinced ourselves, I think, that we should chase this story because there's definitely something in it. And to do that, we need to create a better comparison. So in other words, we should be using the same satellites and same sensors. We should be maybe moving to level 2 data so that we get the exact same pixel and retrieval times. We need to look for more logger data, and indeed I have a lot more logger data that we can play with. We obviously need to locate our satellite pixels close to the loggers, and this is another thing. Actually, this is something I didn't point out. The daytime and nighttime logger data, we just took 6 a.m., 6 p.m. as our cutoff to distinguish local night and local day, and average them. What we should do is narrow that down to better match the actual satellite overpasses, and that might change the story a little bit. Other considerations that might be interesting. Notice that there was a bit of a story in the tidal ranges for Arlington versus dry Tortugas. So do tides alter the logger or the satellite, the logger and satellite relationship, I should say? Is bathymetry a story? In other words, is turbidity a story? Because don't forget, in shallow water especially, you can have high turbidity, and that turbidity can can change the temperature profile through the water. Is there a preferred time relative to daylight or tides for satellite overpasses, for instance, over shallow water? Is there a need for reef-specific cloud detection algorithms? Maybe there is, and maybe, for that matter, there is a tide story in that. And of course, is there a need for reef-specific SST retrieval algorithms? there might be, and I'm not sure that our current comparisons will necessarily suggest that, but it's a question worth asking. So this is very early stages, and that's the beginning of it. Okay, Jonathan, you're up next. I'll mute me, I think. Actually, I can mute it on the microphone I'm using. So go ahead with your bit and tell me when to forward on to the next. So actually, I can do that now. How's that?
Okay, can I be heard now? Hello?
Yes, that's fine.
Yes, okay. Just William didn't react. She's obviously ignoring me.
I've muted. I've been a good boy. Muted.
No, I was watching you. Okay, so the bit that I've been looking at is, as some of you will know, part of my job is to try to apply metrology to Earth observation data. And by metrology, I mean the science of measurement. And by the science of measurement, I essentially mean the way metrologists try to trace measurements back to the SI to try to lock measurements down into an unchanging standard. And some of you may know that the SI has now been redefined in terms of fundamental constants, which are fixed over time and space. So part of the job of a metrologist is to try your best to understand uncertainty relative to, well, uncertainty and error relative to things like the SI. Now, of course, for coral bleaching, that's quite a step. But one of the things that you try to do to understand error in any measurement is basically go backwards through the whole measurement process and try to find the fundamental drivers of error and then propagate those through whatever processes you have to get to your measurand. And then in the case of coral reefs, they then take that measurand to estimate stress, and then you have a biological side of things. So what we're trying to do is basically try to map out what we think the sources of error are in the case of coral measurement, really. And as you can see here, this diagram on the right is an uncertainty tree, and what we mean by that is this is how we try to understand ourselves where the sources of error are and how those error propagate through the system. So at the very top, in this case, you will have your level 4 SST datasets with their uncertainties feeding into the process. As you go downwards through the process, you're breaking it into, well, how do I generate what's known as a degree heating week, which is one of the metrics for stress on corals. So you go through things like averaging over time scales, accumulating information, that you end up with this degree heating week, which is the box in green there, which, like I say, is one of the measurements, and you use it to estimate stress, basically. And then that sort of measurement can then feed in, you then need information. If you're really going to do a metrological analysis, you need to know, well, how is this really related to what the corals themselves are sensing and feeling and reacting to. And so the bottom part of the diagram is our breakdown of some of the biological processes that go into coral stress on the basis of information about temperature. And now, of course, this is where we start moving the temperature from, say, a skin estimate of the temperature down into depth, where you take the bathymetry into account. And then you say, oh, okay, a coral at that position, at that location, I expect the temperature to be X. Maybe you need to fold light in, maybe you don't. And then you worry about how the biological aspects are working. Now, I would say, talking to the biologists, they basically say it's at that level it becomes far too complex, because you can have different genetics, you can have different ratios of different coral species in a very small sort of spatial temporal domain. But I think what we're aiming for is some sort of information flow from the biological side up into what you may set as a threshold. And this would then mean that instead of like now, where you may have a single threshold that tells you, yes, it's going to bleach, no, it's not, you would have a more regionally, temporally specific threshold that would try to take into account some of the other aspects of things that are going on. Anyway, that's the idea. So we've constructed this thing. we've clearly thought about many of the processes, and we're trying to sort of move forward in trying to get some of the information to fill in some of these boxes, because you'll notice that on the edge of every box there, which is a process, there is an associated uncertainty. And of course, you have to estimate those uncertainties. So that's what we'll start doing. Next, can I get this to move?
Now that next one's the last slide.
Oh, okay.
It's worth noting that the uncertainty levels are color coded. Basically, dark blue means that we're pretty certain we can characterize that uncertainty. The light blue colors mean that, well, it'll be a bit difficult, but we think we'd be able to do that. And the orange ones mean we've got Buckley's chance. Notice there's a lot of orange on the bottom and not so much orange on the top.
Yeah, but I would also say that even though it's true at this level of breakdown, we probably have no way of estimating those uncertainties. As an overall system, we may be able to envelope what's going on, in the sense of we know some level of knowledge about what's going on, I would hope. Because if we can't do anything about the orange, then we might as well get rid of the biological side of things, which I think is a bit of a shame. But that may take some thinking about, and I'm not an expert in biology, so I would defer to William and his colleagues on that. Anyway, as William said,
don't refer to me. I don't know anything about biology either.
So I think that's the end of the presentation. So.
Oh no, actually, there's your.
Yeah, I thought there was an extra one. I couldn't move it forward.
Right. Sorry.
But I think we've basically talked over this.
I think we have.
So I'll just leave that. Yeah.
So that's
so